Hi friends, today we are going to see the aerofoil aerodynamics using star CCM plus. So first we will revise the basics of aerofoil and then we will move on to the simulation of the aerofoil. So uh, every object is having the capability of fly. Okay, so the capability of how much it can fly varies for different objects. So an object which has high capacity of flying and very low possibility of getting dragged is what aerofoil. Okay, so such a shape was invented by Da Vinci. So the aerofoil is the cross section of the airplane wing. Okay, so airplane design engineers first choose the aerofoil of what they need first. Depending upon that, they design the total wing of the airplane. So the aerofoils are the very basic thing for aeronautical design. So aerofoil is a shape which has high curvature at the upper and low curvature at here at the bottom. Okay, so this foremost point is the leading edge um, and the and this point is trailing edge, and this end is trailing edge. So a line which just connects this leading edge and trailing edge is called as a chord line, and this chord line uh, yeah and when this is the point of leading edge. When I move in this edge for 5 centimeters, say I am reaching some point at here. Oh, some point at here. So when I move some 5 meter, I will get some point here. So when I draw a line and I make a midpoint for that line and I make that. Okay, so let's end up this one and we'll focus to note. So say I am drawing a line and this is the midpoint of that line and this is the midpoint of this line. So likewise for this is the midpoint. So a line so likewise we have many locus points, and a curve which connects all the locus is called camber line. Okay, before designing an aerofoil, first design engineers they will be going for this camber line. They will draw the camber line alone and they will make a flow over it, and they will calculate a lift coefficient called design lift coefficient. Design lift coefficient. Okay, so this camber line is a important one. Okay, so let me go back to our slide. So this is what a camber line. So this is an unsymmetrical aerofoil. That means an upper surface curvature is not equal to the lower surface. Okay, so we have a camber line. For a symmetrical aerofoil, like what we can see here, yeah, this one. This is a symmetrical aerofoil. The upper and lower both are having the same curvature. So a line which connects the leading edge and the trailing edge is called as chord line. And the camber line also, if I draw, that also fall on the same chord line. So for a symmetric aerofoil, chord line and mean camber line both are the one and the same. So when there is a flow, okay, let me back to our slide. So this is what aerofoil terminologies. So we have explained this, so we can go to the next one. So we have seen that aerofoil has its upper surface more curved, and this this aerofoil, yeah, we can see. So the flow, say at a 10 meters per second, it's entering here. Wait, we will go to notes. Say it's entering at 10 meters per second at here, and it's increasing to 12, say 15, at here, sorry, say 15 meters per second at here, due to this positive curvature, and 40 meters per second at here, and here, again at 35 at here. Since the curvature is going back, the pressure here will be low, so the velocity will be somewhat less in this region. Okay, so likewise it has the velocity. So in the bottom it is 15 at here, and 12 at here, because it's not. So likewise it will be in somewhere also. So the velocity is getting increased in the upper surface in the high magnitude. So velocity, since because of high velocity increases, there is low pressure. So this is what called as Bernoulli's law. So here you can see, when there is a force which is input, this is the free stream flow. Now it is with some angle of attack, say. So let me see what is mean by angle of attack. So that can be well said by this one. So if the flow is coming in this direction, if the flow is coming in this direction and hitting, the angle which is made between the chord line and the free stream flow, airflow, is called as angle of attack. This is angle of attack. It is symbolized as alpha. So for a cambered aerofoil, even if the flow is parallel, there will be some angle of attack, since the chord line will be somewhat if I draw chord line, you can easily understand this one. Yeah, this is chord line. So even if the flow is tangential, it has some angle. You can, if you zoom, you can find out some angle in between them. It is not straight actually. It has some angle, which is what? Alpha. Okay. So this is what you need to know about angle of attack. Now we will move to our slide. So when there is a fluid flow over the aerofoil upper surface, it is getting increase in velocity, so pressure drops. This is according to the Bernoulli's principle. So because of that, there is a pressure distribution. In the upper, the pressure is less, so that is characterized well by the length of these arrows. So in the bottom, the arrow has large length in order to say that the magnitude of pressure at this region is higher. So likewise, we have everywhere the pressure, and we have the pressure distribution around this aerofoil. And when there is a fluid flow, because of the friction at the friction of the solid aerofoil surface, and there will be shear stress production on the aerofoil's outer periphery. So if I just extract a small infinitesimal volume, say dA, then I will have a force perpendicular to it, which is pressure. So pressure always acts perpendicular to the considered area, and shear stress is always acts perpendicular shear stress always acts parallel to the always acts tangential to the considered area. So because of friction, there is a shear stress production, and because of pressure, there is a pressure distribution. So around the aerofoil, we have pressure distribution as well as shear stress distribution. So I will convert this pressure into pressure force, and this shear stress into shear force, and I will add up these two forces, and I will find a resultant force for this total aerofoil. So that resultant force is having this much amount of this this vector is representing a resultant, which is conventional for the aerofoils for this kind of this angle of attack cases. So when I resolve the total resultant force produced because of the pressure distribution and the shear stress distribution in the flow direction, I get the drag. When I resolve the resultant force in the perpendicular direction to the flow, I get the lift force. Okay. Okay, we need to know about the velocity of sound. So velocity of sound is a effect, the sound itself is an effect of molecular collisions. Okay, so we can make a quantify measure of it by using the mathematical correlation found in the aerodynamics. I referred the book by Anderson named Fundamentals of Aerodynamics, and I found this equation in that book, uh, where the velocity of sound A is equal to square root of gamma, it's beta RT, but here beta represents the ratio of specific heats. So the value of Cp by Cv is 1.4, and the R is gas constant, it is 287 kilojoules per kg Kelvin, and the T is the temperature. Okay, so we are in the atmosphere. When we go um, up to the stratosphere, temperature decreases. After the stratosphere, the temperature increases. So the flights are traveling within the stratosphere only. So depending upon the altitude of the flight, there will be the temperature, the outside temperature will be different. So at that instant, at that altitude, the velocity of sound is different. Okay, so velocity of sound differs with the altitude. So this is the thing which we need to know. So now it is our turn uh, to make our attention to Mach number. So as an aeronautical engineer, we need to know the importance of Mach number, because we measure the velocity of aircraft in Mach number only. And because in flight we have a uh, special effect in the flow, like shock wave, that is one key factor for this introduction of Mach number, because when the velocity of the aircraft and the velocity of the sound at that altitude, when these two properties coincides, there is a strong pressure wave generation, where the two velocities coincides. So that shock wave is a big criteria, but that is for compressible flow problems only. But today we are going to solve an incompressible flow over a wing. So however, in our case we don't have the shock wave. So Mach number is also a non-dimensional number. It is velocity of aircraft. Sorry, if it is a aircraft, then it is a velocity of aircraft divided by the velocity of sound at that altitude. Okay, Mach number below 1 is a subsonic, near to 1 is a sonic case, and near to 1 we will call it as transonic also. And Mach number beyond 1 and up to 5 is called as supersonic flow, and beyond 5 all Mach number are hypersonic. And critical Mach number, this is I will explain this with notes. Okay. Yeah, I said earlier that the Mach number which is at the free stream is 0.5. So when the flow is getting accelerated at here, it may rise up to 0.7, say 0.7, sorry, control Z, 0.7 Mach.
At the maximum, this is the maximum it attained, but with speed, and I am getting a Mach number of 1 at here because of the positive camber acceleration.
I am getting a Mach number of 1 at here, at this point. I need to move. Okay, 1 Mach number of 1 at here. So because of that, um, so I'm having a maximum Mach number at here. If, anywhere around I don't have that much Mach number, but so this is the critical Mach number. Even though the free stream Mach number is below, is in subsonic, somewhere in the aerofoil surface, outer surface, we have attained a Mach number of 1. Okay, so this Mach number is critical Mach number. Why we say it is critical? Because if I increase the speed of my aircraft hereafter, that means if I increase the Mach number of my flight, then surely there will be formation of a shock wave in the aerofoil surface. When there is a shock wave, what will happen? The pressure downstream of the shock wave will be very higher. So if the aerofoil has very high pressure at the upper surface and bottom also the same amount, then there won't be much lift. So we need to avoid this shock wave effect in order to overcome the wave drag. Okay, so we have different kinds of drag on the aerofoil, like friction drag and shock wave drag, so and profile drag. However, the basic is drag is due to pressure, uh, unbalanced pressure and unbalanced shear stress in the flow direction causes the drag. So when I increase above the critical Mach number, I get shock wave. That's how I have a very high drag over my aerofoil. So drastically the drag increase from 0.7 to 0.77 is very higher. You can see and CD was very standard. After some Mach number, if I increase the CL, the CD goes higher. Okay, it suddenly increases. So this sudden increase of drag is because of shock wave in the upper surface of the aerofoil. So
So we don't want to go beyond critical Mach number in passenger aircrafts. Okay.
let me go to the PowerPoint. So we have finished the basic essential in aerofoil terminology, and now we are going to solve a real world problem. So the problem for today is we need to simulate the flow over a aerofoil of it is categorized as NACA 0012 for an angle of attack 3 degree. So this is the NACA 0012 aerofoil, and the Mach number for our flow is 0.15. That means our aerofoil is going at a speed of going at a Mach number of 0.15, and where the pressure is 1 bar, and the density of air which is moving over the aerofoil is 1.184 kilograms per meter cube, and the Reynolds number based on the chord length of the aerofoil, and This chord length of the aerofoil is half a meter. This chord length is half a meter. Okay. And we need to calculate the lift and pressure coefficient, lift coefficient and drag coefficient and pressure coefficient distribution over the aerofoil when the flow is at 3 degree. So this is our today's objective. So here they have given Reynolds number. Sorry, this is Mach number. Actually it has been mistakenly given. So it's Mach number. Mach number is equal to velocity of the object divided by the velocity of sound. So we have 300 Kelvin as our temperature, and Reynolds number we have. We don't need Reynolds number here, no? So you just calculate the velocity from m equal to v by a derivation, and you will arrive at 52 meters per second. Here it is by mistake. And we know that Reynolds number is equal to inertial force divided by the viscous force. I just rearranged the equation so that in order to get the dynamic viscosity of air from the Reynolds number. So I am arriving at 1.92 pascals as second for dynamic viscosity. So we have an understanding of the problem. Okay. So this is the step we are going to produce further in order to run the simulation. So first we are going to import the aerofoil geometry, and not only the aerofoil we will be importing, we will import a wind tunnel with the aerofoil, so that we can able to make the flow over the aerofoil using the tunnel boundaries. So then after we will set the physics continuum, that means we will set what is the material and what is the flow type which is being flowing, and if there is a turbulence in the fluid flow, then what kind of turbulence model that we have to use. That everything I will be setting at this phase, and I will set the initial conditions of my domain. In our case uh, the initial conditions are the initial velocity, which is 0.15 Mach. That means it is a incompressible flow. So, and then in order to define the angle of attack for the aerofoil in star CCM, we need to create a Cartesian system which is at 3 degree angle of attack from the local coordinate system. So that I have to do for the analysis purpose. And in order to analyze with the CAD geometry, I need a mesh on the surface. So the mesh, a good mesh will yield at a best result. Okay, so we need a proper mesh at the surfaces in order to capture the important features like leading edge and trailing edge, and in the boundary layer region over the aerofoil we need a fine mesh, whereas near the boundary of the tunnel we need some coarse mesh. So these terminologies you will come to know sometimes after. So however, this is the way I am going to produce further. So I will select some mesh modelers and then I will set some custom surface on the aerofoil surface so that I can capture the physics near the aerofoil accurately. So for capturing the aerofoil flow over the aerofoil accurately, I am choosing these two, and a wake refinement zone in order to find out the wake developed in the flow. Thereafter, in order to visualize our solution, I will be creating some scenes which are essential, and I will create some plots which are our objectives, which is lift coefficient and drag coefficient and pressure coefficient. Okay. In final, I will relate the lift coefficient, drag coefficient and pressure coefficient calculated from the star CCM with a software called Java file. Okay. So that is our final stage. So this is the methodology I am going to use. So in the outer, actually our aerofoil is located at here, which is NACA 0012 of having 0.5 meter chord length. So my domain size is at here it is 5 times the x in the forward, and in the backward it's 10 times. Not this is 5 times, it's 3 times and it's 10 times. Okay, so it's a bullet shaped domain which it is conventionally used for aerodynamics, external aerodynamics over the aerofoils. Okay, so from this uh, surface, the velocity will the air will be entering at some velocity, and at this surface, through this surface the total airflow will be getting out. So, and this aerofoil surface will act like a wall, so that in a wall, when there is a flow, there will be a boundary layer formation. So we are interested in that only. So in such a way I am producing my boundary conditions. Okay. So near the aerofoil, in order to capture the boundary layer effect, I am going for a mesh modeler called Prism. So this will be uh, useful, and we can use polyhedral measure also, but today I am not going to use polyhedral measure. I will show it in the next one, and I will use trimmed measure. Okay, so end our show right now, and we will start the star CCM and see all those things practically. So start star CCM. And file, new simulation, and it is serial. Click OK. Now import the surface mesh, which is located in create a new part with default settings. Automatically a geometry scene will be created. Okay, so this is the face through which this is the body which I have. So the total space which we are seeing is a space, and this is our object of interest, which just occupies some dx and dy and dz. So this object, which what we see, is a fluid. So I need to set that. So before that the imported IGS file will be in the parts menu. So I will expand that, and this part is having several surfaces, but all are combined as of now. So I need to split according to use it in the boundary conditions. So I will go and right click over there and split by patch. So I will call this face as a right side and that face as a left one, and these two are inlet, this one is outlet. Create, and the remaining one is aerofoil. Okay, so the chord length of the aerofoil is half a meter, so I will measure that and show, and I have maintained 8. I have maintained nearly 3 times the length in the forward and in the back. I have used 3.5, so 7 times. So totally my domain is this much dimensions. Okay, now we will go to feature curves and edges and split this also non-contiguous. Okay, so this edge is aerofoil edge. So these two we can combine, no need of two. Okay, so now assign this part to regions, right click and create a boundary for each part surface and create one region for all parts and click apply and close. So a region node will be added. So in that we have our aerofoil and our inlet and left and outlet and right. So if you want to see a close view, you can have. So be clear with the geometry, and you can turn on your mesh on and off. So as of now we have not performed any mesh operations. So the triangles which we are seeing right now is tessellation. It is not the mesh actually, so we will mesh this part sometimes. We'll mesh this part after some time. Okay, so before meshing we will create the physics continuum. So we go to physics continuum, and this model is 3-dimensional and a steady flow, and gas is going to flow over there, and it is a segregated flow, and it is a constant density, it is incompressible flow, and in it is turbulent. And in order to capture the turbulence I am going to use Spall-Talmaras and click close. So we have set the physics conditions. However, as of now we have the domain in 3D, but I am going to solve this problem in 2D. So I have to convert the total domain to 2D once after the volume mesh is over. Till that I have to maintain the three-dimensional things. So why I have set the physics continue at first? Because when I am going for meshing, so this surface is a wall right now, and this is also as a wall, so it is not as inlet or outlet. So if I choose a mesh modeler, uh, and many mesh modelers will do a fine mesh near the walls. So as of now we have every surfaces as wall. So if I mesh with using the star CCM mesh modelers in the mesh continuum mode, then it will give a finer mesh wherever uh, it is unnecessary. So I need to set the boundary conditions uh, for that. So for that, in order to set the boundary conditions with full details, we need a physics continuum for that purpose. So only I have created this physics continuum before setting this before operating on mesh. So go to mesh and select this as wall and this one as velocity inlet, and click close, and this one is left and this one is your right. Click both of them and click these two as interface, and expand the interface node and double click there. It is a periodic interface with translational periodic, and click close. That means these are not walls, these are just enclosing the volume, that's it. It is an interface, okay, and this is outlet, and one more surface which is hidden is this is our inlet. So we need to define the outlet. Edit, this has to be outlet of pressure outlet. So so this is our domain, and we have set the boundary conditions. Till now you please remind that we have not input the velocity into our domain. So in order to define the angle of attack and the velocity of the airflow, so I need to generate a coordinate system. So I am going to tools and coordinate systems. I will expand the laboratory and local coordinate systems, and I will make a new Cartesian coordinate system which makes its origin at 0 0 0, and I am going to align the I direction. So my aerofoil is at angle of attack 3 degree. So at the Y, then sine of 3 will be appearing. So sine 3 degree will be 0.052335. So click there and click renormalize. So the coordinate system will be updated according to the coordinate unit vector direction, and click create once and click close. So our Cartesian system is ready. So you can rename if you want, instead of rename it as angle of attack 3 Cartesian. Okay, so we will go to our physics continuum node. So we will do this thing later. So before that we will make our mesh model. New mesh continuum. So I'm going to select the meshing model as surface remeasure and a trimmer measure with prism layer measure. Close. So I will expand the mesh values. Base size of mesh to be, wait, I will expand everything. So base size of mesh is going to be my please remind that my aerofoil chord is 0.5 meter. So I'm putting 0.2 on the base of this knowledge. I'm putting 0.2, and maximum cell size can be of 200% of the base size. So this is base and it has been multiplied by the factor of 2. So this is the maximum size I may see in my domain. And maximum number of prism layers, I need a 20 prism layers, and prism layer thickness is relative to base. It is 33%. That means up to 0.06 meters the prism layer will be grown on over the wall. Okay. Oh, let me reopen that thing. So number of prism layers we have set. Prism layer stretching, you just use a factor of 1.2, and surface growth rate 1.3, surface proximity it can be okay, and surface size. Here you specify the minimum size of the element which is near the corners. So I set a value of 10% and relative target size of 70, and template growth rate, default growth rate to fast and boundary growth rate to slow. Okay, close. So these are the things which we need to input, and we need to capture the this aerofoil surface finely, no? So I will expand that in the regions, and I will custom surface mesh I need here. So I will double click over here, and I need a custom surface mesh and custom boundary growth rate. No need of boundary growth rate. Okay, so mesh values, we need a minimum size of 2% and relative target size of say 4. So I am making a fine mesh at the aerofoil surfaces, and after that I am going to take up the wake region. So I go to the mesh conditions, mesh values, and trimmer wake refinement, and click a new wake refinement zone, and this has to be 5 meters from the trailing edge. So it has to be from the aerofoil and it has to be grown in the x direction, and boundary growth rate to slow, default growth rate fast. Okay, this is 10% in the wake regions. Okay, click close. So these are the necessary things in this mesh So just click the generate volume mesh once. It generates the mesh. It just takes some time. The mesh is being created. It is showing the status at here. It is generating the prism mesh. Yeah, volume mesh is finished, and we need to apply the volume mesh. See, I have very fine mesh near the wall. Okay, and I have a wake refinement zone which is also well created. This is what I need. So this mesh is adequate for capturing the effects for this study. Okay, so I will go to the next step. I will just convert this total 3D domain to 2D domain. So before that I will save this. So go to file and save the simulation in a folder. So we will name this as flow over NACA 0012 3D mesh. So it contains up to the 3D mesh. So save this. And hereafter I am going to convert my domain to 2D. So go to mesh and convert to 2D. You select the regions and select this tick mark, delete the 3D regions after the conversion and click OK. Once you click OK, it is it has just generated the 2D mesh which we are not. Okay, I will create a machine so that you can view that thing. So this is our aerofoil, and this is what I need for my analysis. So immediately after the conversion of 3D domain to 2D domain, there will be a node appearing for physics continuum automatically, which will be created with 2-dimensional model. So hereafter I don't require this 3-dimensional model, so I will just deselect all those models and I will delete that thing. So right click there and select models and deselect everything. Deselect everything and click close, and now you delete this physics continuum and then expand the regions mode and boundaries mode, and now you choose the velocity inlet and set the value of velocity. So we need to, the velocity is in the direction, so is in a 3 degree to the local coordinate system. So I have already generated a local coordinate system which I need at 3 degree. So for that I am expanding this one and select this two components and go to physics values and flow direction, method to coordinate system to angle of attack 3 in Cartesian. So in this Cartesian coordinate system my flow is going at x-axis. Okay, so this is what my x-axis. So my flow is going in the axis and with a magnitude of 52 meters per second. This is what calculated from this one. This is m actually. I will make the correction here. Mach number is equal to this one. So here are 287 kilojoules per kg Kelvin. Kelvin. We know the m 0.15, you input that and we will attain 52. So that is what I input here. The velocity magnitude 52 at 3 degree angle of attack I have said. So through this inlet the air is going at 3 degree angle of attack. Now go to outlet. So there is no need of any specifying any special conditions there, right there. And in order to choose some initial conditions of within the domain, you expand this physics 1 node and go to reference values, initial conditions, and initial velocity in the domain was also, I am assuming that it was also on the uh, local coordinate system which I have. So it is 52 meters per second on this coordinate system. Okay, so this is the initial condition I have for my problem, and I have gas as my material, and I need to check out my material property. So density is 1.18415, which is what given. Okay, 184, and pressure is 1 bar. So expand the value and reference pressure, it's okay, it's also 1 bar. And then add Reynolds number, okay, we cannot check it right now. And then we need a dynamic viscosity of air to be 1.9 e power of -5. So just we will use this dynamic viscosity for our analysis, 1.8 e power 5, 1.92, and click close. So this is how we have set our material conditions and our initial condition in our domain, and I have all these relevant things. And hereafter, so till now we have set these conditions. We have set the material and flow type, and we have selected the turbulence model, and we set the initial conditions, and we set that angle of attack, everything, and we run the surface remeasure trimmer prism, and we have finally a good mesh with proper physics settings. Okay, hereafter we need to focus our attention on the creating the post processing aids. So I am going to create the scenes by right now. So going to this icon will help us to create a scene. So I am going to create a scalar scene on this two-dimensional domain, and this is going to be velocity magnitude. Okay, and I will make one more scene which is for vector. So this is vector scene. Okay, and I need hereafter only plots. I need plots, lift and drag coefficient of pressure. Okay, so for that I am going to first generate a report. Click new report and go to force coefficient. Okay, in order to calculate lift coefficient, so I will go to notes. In order to calculate the lift coefficient, we need a formula, half rho v square s into CL This is the formula for lift. Half rho, it's not P, actually it's rho. It is mentioning density. So half rho V squared, S is a area which is
wetted surface area to the flow. So this is the area which we have to calculate from the star CCM software. So my vectored surface area, I need to measure the area in the local flow direction. So the aerofoil will have some surface area on the top and bottom. When it is projected on the flow direction, what is the area? That is where the flow is going to be attached. So this is wetted surface area. So I am going to calculate the wetted surface area first of all. So for that I need to make a special report called frontal area report. So from that I will get this value, and after that in order to calculate lift I need density. So I have already input the density, and I need a velocity, and the software calculates the CL, and it calculates the lift based on this thing. So likewise for drag also half rho V squared S into CD. Okay, so first of all I am going to star CCM, and I will save this simulation as 2-dimensional, and I will click report and new report and frontal area. I need to edit. I need the frontal area of aerofoil parts, aerofoil only, on angle of attack 3° thing, and I am viewing up in X direction. In this coordinate system I am viewing in X direction, with where its normal is located at Y axis of this coordinate system. So this is what I have input. So click close and run report. So from here I can get a reference area which is needed for the analysis, so needed for the calculation of coefficient of lift. So if I go to notes, yeah, this is what the value of S. So it is 0.499. I can call it as 0.5 also, roundly 0.5. So reference area is 0.5 and it is 52 and it is 1.18. So I know these three values. So software will calculate the coefficient of lift, and from that it will relate to the lift force generation. And likewise for drag also. So I will generate a new report, force coefficient. I will rename this as lift coefficient, and I will edit. I need to measure the lift coefficient, that will be in Y direction. Okay, and I need it is a combination of pressure and shear average. So in order to calculate the lift I need a pressure that was initially given. So this is I don't need to input the pressure here, because in the initial condition itself I have given as 1 bar. So in the reference density you just input it as 1.184, and in reference velocity we need to input 52 meters per second, and in reference area we need to input 499 or otherwise 0.5 simply. So I need to measure on aerofoil. That's it. We have set everything needed for the measurement of lift coefficient. Click close and just um, right click left click the lift coefficient and drag it over the reports, so that a copy of the lift coefficient will be generated, and just rename this as drag coefficient and edit only the direction. Drag will be in the x direction in the local coordinate which we specified, and its units will be in it doesn't have unit, it's a unitless, and we need a I'm also generating a force coefficient which is lift force, and edit the parts to be uh, units Newton, coordinate is this one, make this as 0, and lift will be in y direction, and reference pressure we don't need that to input, and on the solid aerofoil. Okay, close, and you make a copy of it by dragging over the report and make it as drag, and this will be on x direction, on the aerofoil. Okay, so everything we have set. So one more thing, we need to measure the pressure coefficient. So for that I will make a plot, right click over there and new plot, and select XY plot and rename this plot as pressure coefficient, and X type to be the direction, to be the scalar of position, magnitude, and click OK and click close. And in the Y type we are going to choose a function of pressure coefficient. So we are going to measure the pressure coefficient along with its position in the coordinate system. So I need to edit, I need to measure those on the aerofoil surface outer. I'm expanding the left axis because it is conventionally this axis will be reversed for the CP plotting. So I am going to left axis, and click reverse and click close. So this is all we need. So we have set the proper boundary conditions, we have a good mesh, we have necessary plots to see our outputs. So everything we have set. Now it is time to run our analysis. Before that I will initialize this thing. So we can see that it is blue color is indicating 52 meters per second. So it is what our initial velocity in our domain. So I can go and see the vector scene, and just I will edit this vector scene little bit, save the simulation and go to vector scene and display as, and expand this vector and glide display as, expand this vector 1, tangential, line width to be of 0.2, okay, and these are all okay. It's constant length, vector spacing uniform on the screen, glide tip scale 0.5, 0.3, adjust it. Okay, uniform spacing 50 by 50, okay. So click close. So we have our vector scene ready. Now I will make some corrections in here itself. So I will go to pressure coefficient and I have 0 as of now. So I will click run, and I have to create the plots from the reports. So just select all those things and accept frontal area and click create and monitor from report and multiple reports and run the simulation. And you can watch all those things. See, the velocity is okay. Here we have our velocity distribution. So in the upper, from 52 it has been accelerated to 72 at here, and somewhere here and all we have a velocity of 44 at here, and so from that we can easily suggest that this is how the flow has been going and the wake region has been finely captured. You can see this thing. Okay. So still the iteration is running. I have made one mistake. In order to calculate the pressure coefficient, I need some reference values. So I need to input that in tools, field functions, and in the center of pressure coefficient I need to input the reference density to 1.184 and a velocity of 52 meters per second. So this is the thing which it requires. So the pressure coefficient has been calculated, and it's so, and also one more thing, I need to change the vector C little bit. go to vector scene, click displays and vector scene, glide tip scale 0.1, okay, 0.01 or no, 0.5, sorry, 0.05, okay, it's enough. And constant tip size, so we can generate a another one, vector C, displays vector, go to that, line width to 0.1, sorry, 0.5, and then you can use parts is region 2D, and you can use this as a part, sorry, this region 1, vector field, its velocity and its color bar properties and its glide. So this is the thing which we need to understand. Constant length, uniform on the screen, use absolute size, part size, direct, part size. Glide tip scale, to be 0.05. However, there is, you don't feel any change it all. So this is how, and we can start running our simulation. So we have a lift coefficient, yeah, iteration has been finished, and we have a lift coefficient of, we will measure that, just lift coefficient monitor plot and click open. So otherwise we can expand this one, and no, you go to report and run the report. The drag monitored was 0.011. You copy this value, so this is our result. So CD is 0.011 and CL, this is our results. Our CL we are going to find right now. So this is yeah, lift coefficient, run the report, and lift coefficient is 0.31 we copy this one and paste here. So this is the CL and CD, and lift is 248 newtons, 250 newtons, around 250 newtons, and drag a drag of 9 newtons. Okay, so these are our objectives, and we can see the coefficient of pressure also. Okay, sorry. So I have calculated the lift coefficient and drag coefficient, and I have plotted the pressure coefficient distribution also. So this is the I will show the plots. So I have run the flow analysis. So this is my plot. I will change my plot annotations. Lift coefficient, okay. So lift coefficient axis, bottom axis, it's okay. Left axis I need to adjust from log the minimum and maximum. Minimum is 0 and maximum is 0.3. Say sorry 0.4, so that we can get a clear view. So click close. So you can take a view of this and place that in your PowerPoint, like what I have did earlier. So this is lift coefficient plot, which I have took from the thing, and likewise drag coefficient also. I will adjust the plots in such a way that I can easily view the reading of the property which I am interested. And this is the pressure coefficient distribution. So we have our all values necessary for our analysis right now. So I have certain result. I need to compare this result with some other resource. So for that I am just going to save this simulation first of all, and then we can go to Java file, and I need to create an aerofoil of NACA 0012, which is having no camber. Okay, so this thickness is 12. So this is NACA 0012, and I have 81 coordinate points of it. So from this software only I took the coordinates and developed my total design. Okay, so I'm going to design for angle of attack of 3 degree. So this is the pressure distribution. So just compare this one. We have CL value of 0.36, and here we have 0.31. Somewhat it's near. And for drag it is 0.011, and we have the same one, 0.011. Here also 0.011. So Java file also says the same, and in the lift I have some difference between the Java file and my star CCM result. It may be the mesh which I used may not be adequate to capture the lift coefficient and the physics. It may be the reason for this shortage. Okay, so we have our CP distribution. We will check it out with our star CCM result also. Pressure coefficient, yeah, see, it is also same like that,
and it is varying from 1 to -1, and my chord length is 0.5 meter only, so
it is also varying from 1 to -1, and here the chord length is 1, so the graph profile looks to be the same. So this concludes our flow over the aerofoil tutorial. Okay, thanks for watching. Have a great day. Thanks.